Hello class, welcome to the Stat 511 Week 1 video. In addition to talking about the basics of this course, we are also going to talk about the basics of statistics. So let's first talk about our class organization. All the information you need for this course can be found on eCampus, such as the syllabus, lecture slides, videos, assignments, and gradebook. About once a week, you're going to receive a message from me that will tell you what you should be working on this week, and you'll also be informed of any assignments you should be working on or ones that are due. Okay, so that brings us to the end of course organizations. You're going to hear me repeat this phrase a lot, but if you have any questions, please send me an email. I do try to be pretty responsive with your emails when I see them. I try to answer them pretty much as quickly as I can. Now that we've covered all of the class information, we can now begin talking about the class material. This lecture is really going to be focused a lot on the very basics of statistics. Quite a bit of this is going to be review material for you guys, which isn't a terrible thing for the first week. Beginning of all my lectures, I like to have a list of objectives that are covered. I personally think this helps you when you go back and are trying to study. You can look at one of the very first slides and say, okay, this lecture slide has these topics. This isn't what I'm looking for. Go for the next week. So in this video, our objectives are going to be what is statistics? We're going to talk about the importance of logical data structuring, types of variables, and we'll finish off with some frequency distributions, graphical displays, and measures of spread and central tendency. So to begin, what is statistics? Well, statistics in our topic of discussion in the whole eyes of the course is the science of collecting, organizing, and interpreting data. Now, what is data exactly? It is a collection of observed values representing one or more characteristics of some objects or units. Now, this course is a bit challenging in the sense of I don't feel that any individual topic is something particularly hard. What is challenging about this course is just like mathematics has several subjects like geometry, algebra, and statistics, well, statistics itself has various sub-subjects. And this course takes pretty much all of those sub-subjects and gives you just a spoonful in this course. So it is a lot of information on various topics thrown at you all at once. It does all come together, but it can at times be overwhelming. But it all comes back to what is statistics? It is the science of collecting, organizing, and interpreting data. Well, there's a lot of different ways of collecting data, organizing data, and interpreting data. My goal as your instructor is to give you a spoonful of those different topics and different options. Now, to begin, let's talk about the data structuring because being able to look at data and understand what you're looking at is pretty important. So we have some information that is collected on various subjects. A variable is a characteristic that differs from one subject to the next. Examples include age, grade level, numbers of hours you study, score on a final exam. The list is infinite. The values of our variables that we obtain are the data. An individual value is called an observation. And then all of that information put together is what forms a data set. The organization of a data set is very important. If you look at this data set, it's very jumbled. And to be honest, you probably don't know what you're looking at right now. You see names, locations, n's, y's, numbers, decimals, things that mean absolutely nothing. There's very little that we can even obtain from this. But organized properly, we can actually tell a lot of different information from a data set in the individual observations. Organized in a much better layout, we have logical headings and organized information. We now see those crazy looking numbers before were an order number, which correspond to a name, where our order was made, price, area code, download, gift, ASIN, and artist. So now looking at this, I'm going to say, this is probably a data set of people who downloaded music. Say, for example, we have an individual named Catherine H. Her order number we have, she probably bought a song by Coldplay for 99 cents. She lives in Ohio in this area code. And she had the option of, was it a gift for somebody or not? So organized correctly, our data can make a lot more sense. Now, talking about each of our individual observations and the variables, this can, of course, be pretty complicated. If I scroll back to the data set we were just looking at, lots of information, and each of these informations can be further classified. So our third objective is going to focus on different types of variables. Now, one important factor that influences our variables is what kind of study was conducted. Was it an observational study or an experimental study? An observational study is one where researchers observe the effect of a risk factor, diagnosed a test, treatment, or other intervention without trying to change who is or who isn't exposed. An experimental study is one where researchers impose treatments and controls on the process and then observe their results and take measurements. So what is the essential difference? Well, observational studies, you have less to control. It's you're watching what occurs on the world. The experimental studies are designed. So for us, we have types of variables. Two types of variables that we can all define everything as either qualitative or quantitative variables. Qualitative variables are variables that yield non-numerical information. These are also known as categorical variables. Quantitative variables are variables that yield numerical measurements, and the quantitative variables can be either then classified as discrete or continuous. So let's start by looking at discrete variables. So this contains a finite number of values. So it records typically the amount or degree of something. So some examples might be the number of coins in your wallet or the number of animals in the zoo. On the other hand, a continuous variable contains numeric variables that have an infinite number of values between any other two values. So this typically records something that has an infinite number of possibilities, such as the length of time waiting for a bus. Next, we have ordinal variables. An ordinal variable is a variable that reports order without natural units. So something like the 5-point scale or an Olympic rank. And sometimes this can even be quantitative by using a rank number of a scale of 1 to 5. This brings us to the last objective of this first lecture video, and the one that we're going to spend the most time focusing on, which is frequency distribution, graphical displays, and measures of central tendency. So first off, let's talk about the frequency distribution. A distribution is the way in which a variable's values are spread all over possible values. Discrete variables have values that are categories, which we know as before. So the frequency of a category is the number of times it occurs in the data set. The frequency distribution is presented in a table that gives the frequency for each category. So let's take a look at an example. A computer retailer compiles a list of the types of computers sold to the last 50 customers. So we have a desktop, laptop, notebook, or a tablet, and their corresponding frequencies. The relative frequency distribution gives the proportion of observations in a category So we can see for the relative distribution, meaning it is relative to the total. So for a desktop, there was 11 desktops sold out of 50, which would make it 22%. Now we can show our frequencies and our relative frequencies in a number of ways. One of the common ones is a bar graph. We know that bar graphs generally have rectangles of equal width with one rectangle for each category. Heights of the rectangles represent the frequencies or relative frequencies of our categories, and we have spaces between each of our bars. Take a look using our desktop, laptop, notebook, and tablet data, and we can see the similarities and differences of our frequency and our relative frequency bar graphs. Another option is to use a pie chart, and a pie chart is a circular divided such that each wedge represents the relative frequency of a particular category. So for example, if a category has a relative frequency of 0.25, then its wedge should take up 25% of the circle. So once again, using computer scales, we can have a pie chart with each wedge representing the correct portion. There are many ways we can draw a pie chart, particularly using things such as Excel and various other softwares. So talking about frequency distribution and classes. So to summarize, continuous data in order to summarize continuous data graphically, we tend to divide these things into classes. And classes are intervals of equal width that cover all values observed in the data set. So for example, we could be classifying people by age. For example, we could say put the category from people born to the age of 4 in one category, and then so on. The example on the right is the distribution of ages for those who are aboard the Titanic. In order to graph something that is continuous, we tend to favor a histogram, which is a graph that displays the distribution of our quantitative data. Notice that there are no gaps between the bars unless there are 0 observations in that class. That is a very good way to tell whether you're working with discrete or continuous data. If you see a bar graph, it's discrete. If it's continuous, then it's a histogram. Now, there is always a choice when we're talking about how we make our classes, and that is to tell us how we want to make our bin width. So different bin widths can tell many different stories, and we will choose the width that best shows the important feature. So for example, still taking into account our Titanic data set, we can make on the left where each bar represents 2 years, where on the right, we see each bar representing 20 years. Again, all depending on what we're looking for will tell us the correct bin width to use. So if we just want to have a general idea of ages of people aboard the Titanic, we might want to use a wider bin width, and we can say, okay, most of the passengers were between 20 and 40. If we're looking for more detailed information, then we may be more concerned with what is our graph on the left. Histograms play a pretty important role in statistics. We use them to check assumptions, and therefore we spend a bit more time talking about histograms and how to read them. One thing we concern ourselves with is the concept of being symmetric. So a histogram is symmetric if its right half and its left half are a mirror image of each other. Very few histograms are perfectly symmetric, but many are what we call approximately symmetric. And as we can imagine, sometimes instead of having something being symmetric, we can have something that is skewed to the left or the right. When something is skewed to the right, it is also known as being positively skewed. When it is skewed to the left, it is negatively skewed. There is a little rhyme when trying to figure out which way is which. And that is, if you think about skiing down a mountain, which direction would you be skiing in? Well, if we have our little person skiing, going down the mountain, they would be skiing to the left. Ski left, skewed left. Ski right, skewed right. Just a little helpful way to remember and how to keep your skies and skews straight. Next, we concern ourselves with modes. Now, I know you guys are thinking modes in the sense of a measure of central tendency that's been used, where you want to think about numbers that repeat in a data set. Usually mode, you know, is the number that occurs the most. Well, in a histogram, it is still numbers that occur the most, but this is in the visual sense. And we concern ourselves whether we have something that is unimodal, meaning we really have one value that distinguishes itself from the others, or do we have something that is bimodal, where we have two values that are really distinguishing themselves as being something that occurs the most. So for example, if we take a look at this histogram of current salary, we can ask ourselves, is this symmetric? Is it skewed? Is it unimodal? Or is it bimodal? Well, our left and right are clearly not a mirror image, so it is not symmetric. Therefore, it's skewed. How is it skewed? Well, again, think of our person skiing. He's going to be skiing to the right, so it is skewed right. And it looks like we only have one mode, so it is unimodal. This is a very good interpretation of that histogram. Now, we've taken a look at a lot of the graphical displays, not all of them, but quite a few of them. Now this brings to mind to talk about some of those measures of central tendency, and most of these, if not all of these, are going to be familiar to you. So starting off with the basic, talking about our sample mean. In statistics, we do kind of show this in a more abstract or theoretical sense, but it is still the same mean that you've always known. So we like to suppose that observations in a sample are generically x1, x2, all the way to xm. Then we denote the sample mean to be a lowercase letter with a bar over it, in this case x bar, and we know that it's equivalent to the summation of xi over n equal to our x1 plus x2 plus ... all the way to plus xn all over n. So this funny looking E, that is the Greek letter epsilon, and it means, for us, summation or to add. Anytime you see that symbol, we're adding. In statistics, a lowercase letter n means sample size. It's the number of values in a sample. So in order to find the sample mean, we add up all the observations in our data set and divide it by the number of observations in our data set. So if we want to do a quick example, we have 5 quizzes for your biology class. The scores were 78, 83, 92, 68, and 85. We would add up those scores, divide by the number of scores, which is 1, 2, 3, 4, 5, simplify, and we would have a sample mean of 81.2. Next measure of central tendency we'll focus on is the median. And this splits the data set in half, and after we order our data from least to greatest, we can find our sample median. We represent this with still a lowercase letter, usually X, and instead of having a bar, we have a tilde, which is that little curved line. There is two different ways to find our sample median. It depends on if our values are even or odd. If we have an odd number of data, then it is after organizing our data in increasing order, it's the value directly in the center. If we have an even number of data sets, then we have to take the average of our two middle data observations. So quick example. So if we have our data set for our quiz scores of 78, 83, 92, 68, and 85, we would arrange this in least to greatest order. There are 5 observations, so that is odd, so it's simple. It's the value in the center, which is 83. If we have an even number of even number of observations, start the same, arrange it least to greatest. We know that since it is even, we need to take it down to our middle 2 observations. And where's the halfway point? So 15 plus 19 divided by 2, our median is going to be 17. Now, in statistics, we do like to have things be related to each other. A statistics rarely stands on its own. It needs to be in relation to something else. What is it telling us? What does it mean? What is its purpose? So one thing we care about is what is the relationship between the mean and the median? In your high school and middle school, junior high, when you've been learning about median and mean, usually your teachers put more of an emphasis on the mean. In statistics, we do and we don't. And what do I mean by that? Well, if you're looking at a data set that is symmetric, then your mean and your median should be approximately equal. When your distribution of data is skewed, your mean and your median are not going to be equal. The mean is something that is very sensitive to outliers or more extreme observations. So if we are talking about saying that this bottom x-axis is a number line, your median is going to be closer to the peak of the unimodel, where your mean is going to get dragged towards the other observations, or the more rare but extreme observations. When we're dealing with a data set that is skewed, the median is honestly a better measure of central tendency than the mean. So in that case, statisticians care more about the median than they do about the mean. But when we're learning about things theoretically and in a perfect world, which is what we generally like to make classrooms, so generally like how we like to idealize our classrooms, everything's going to be symmetric, everything's going to be perfect, and so yes, the mean is going to be our central focus. Now, what also can be a big factor for us is not just how something measures in its center, but also how our data is spread out. So we do care about the spread. Meaning, is our data going to be located all towards the center? Is it this something that is symmetric where pretty much all the values are clustered at one point and then there's a little bit on either side of our cluster, or is our data more flatlined? So to show that visually, is our data more centered, or do we have more of an even distribution across a larger range of data? So this is why we really concern ourselves not only talking about the center of the data, but also how far it spreads out. One common measure of spread that you all are aware of is the range, which is the difference between the maximum and minimum values. So if we take a supposed age list of guests at a dinner party, we had people that were 16, 18, 23, 23, 27, 35, and 74. The range would be 74 minus 16, the oldest guest minus the youngest guest. So we have a range of 58. But that's not the only thing we can concern ourselves with. We can also talk about percentiles and quartiles. So percentiles divide our data into 100 groups. The nth percentile is the data value such that the n% of the data lies below the value. For our large data sets, our median is our 50th percentile. We usually then concern ourselves with the median of our lower half of our data, which is the 25th percentile, and the median of our upper half of our data, which is the 70th percentile. And together, the 25th, 50th, 75th, and of course the 100th, those are our quartiles. Another type of range that you're not as familiar with is something called the interquartile range, and is the difference between the upper quartile and the lower quartile, meaning it's the difference between your 75th percent and your 25th percent. So what it does is it tells us the spread of that middle 50% of our data, which can be very helpful for us because it can tell us whether most of our data is clustered in a very small group or is it going to be more spread out. One visual representation that we use when we're looking at the median and our other quartiles is something called a box plot. In order to construct a box plot, we usually say it represents the 5-number summary, but it represents the minimum value, the maximum value, your median, quartile 1, and quartile 3. Our maximum value, we consider that to be our 100th quartile. So, what does a box plot look like? Well, here's a nice visual representation of it on the right. The box forms that middle 50%, that interquartile range, and our whiskers are the minimum value to Q1, our 25%, and then our second whisker is the 75% to our maximum value. And what this does is this just gives us an idea of the visual spread of the data. Is most of our data clustered in one section or is it more spread out? So we can take a look at this box plot and we can see that 25, 25, 25, in other words, 75% of our data is located between 0 and a little over 20. The rest of it, notice that we're talking about average wind speed, so that last 25% spans from 2.28 to over 6. This tells us, looking at it, that our data is skewed. Most of our data is clustered from 0 to 2, and the rest goes from 2 to almost 7. Another measure of spread that is very useful and something we use a lot in statistics is called the variance. So the sample variance is a measure of how far the values in a data set are from our mean on average. So the sample variance is denoted with a lowercase letter s squared, and it is equivalent to the summation of the quantity xi minus x bar and quantity squared all over n minus 1. Breaking this down, xi is how we denote an individual observation. Again, x bar, that's our sample mean. And n is our sample size. So what the variance does, as it says, it measures how far a value in the data set is from the mean. Okay, how do we measure distance? We subtract. So what they do to calculate variance, and what you're going to do, is you take each individual observation in your data set, subtract it from the mean, that gives you your distance. And because depending on how you subtract, you may have negative values and positive values, that makes it very difficult when you're trying to understand distance, because, what is a negative distance? So what we do is we square it, because once we square anything, it becomes positive. So that gives us a way to measure distances uniformly, whether something is below or above. We can get rid of that negative sign and just say, okay, what is the actual distance from the mean? And then we divide it by our sample size minus 1. Now, again, let's take a look at how we can see this visually. So something that has a small variance measures variability and spread. Something that is a small variance means there's very little spread. Larger variance and an even larger variance. Usually in statistics, we like having our data to have a low variability, because then we can usually predict better. But of course, that doesn't always work that way. So let's take a look at an example of variance. So this table represents the average monthly temperature in Fahrenheit for the cities of San Francisco and St. Louis. So just looking at the data in general, or if you know anything about those locations, San Francisco, their temperatures stay pretty consistent all year round, meaning it has a very small spread. Our values are close to the mean. Our variance is going to be pretty small. St. Louis, it has a much larger spread. That means our values are going to be more spread out from the mean, and our variance is going to be larger. Another measure of central tendency we examine is the standard deviation. The standard deviation is closely related to variance. It is just the variance after we take the square root. So square root of the variance is the standard deviation. Why do we use this? Well, sometimes certain formulas call for the standard deviation as opposed to the variance, and it can also be easier to understand the standard deviation than the variance. In the variance, as I said before, sometimes when we're looking at distances, we just want everything to be positive. We don't care if something is above or below the mean. We just care how far away it is from the mean. When we want to have that idea of direction, whether it's above the mean or below the mean, then we tend to use standard deviation. Now, as far as our procedure for computing the variance goes, I pretty much already walked you through it. Step 1, compute your sample mean, then go through, subtract each individual observation from the mean, square them, add them all together, and then divide by n minus 1. We can go through and do a quick example. So a company that manufactures batteries is testing a new type of battery design for laptops. They measure the lifetimes in hours of 6 batteries, and the results are presented in the following table. We are asked to find the sample variance of the lifetimes. So our battery lifetime, we have 6 observations. They are 3, 4, 6, 5, 4, and 2. To start off, we are going to calculate our sample mean. So we are going to add our 6 observations together, 3 plus 4 plus 6 plus 5 plus 4 plus 2, divided by 6. So this will give us a sample mean of 4. Step 2, we're going to go ahead and subtract each of our individual observations from our sample mean of 4. 3 minus 4 is going to be negative 1. 4 minus 4 is 0. 6 minus 4 is 2. 5 minus 4 is 1. 4 minus 4 is 0. And 2 minus 4 is negative 2. So notice we have a mixture of positive and negative numbers. Negative numbers indicate it's below the mean. Positive numbers indicate that it was above the mean. Now at this point, we can square our differences so that all of our values are positive. -1 squared is 1, 0 squared is 0, 2 squared is 4, 1 squared is 1, 0 squared is 0, and -2 squared is 4. Step 4, we can add our squared differences together, and this will give us a sum of 10. Last step, we can divide by n minus 1 to give us our total sample variance. So 10 divided by 6 minus 1 is going to equal 2. So our variance is 2, which if we look at our data, we said that the average was 4. If I put this data in least to greatest order, we have 2, 3, 4, 4, 5, and 6. We are saying from our sample variance that the average spread from the mean is 2. Well, our mean here is 4, and above the mean we have 5 and 6, that's 2, and below 3, 2, that's also 2. So it pretty accurately measures the spread in a way that is not necessarily something you've seen as frequently as range before. And if we desire to, we can take the square root and get our sample standard deviation, which would be the square root of 2. Now let's talk about the relationship between our standard deviation and histograms. Remember, standard deviation variance is a measure of spread, and if we were to graphically take our data and turn it into a histogram, then we can visually see our spread. So by taking a look at our histograms, we are asked to order the histograms below from smallest standard deviation to the largest standard deviation. So values that have less spread are going to have smaller standard deviations. For our histogram C, most of the data is clustered around 4 to 6 or 5. So this is going to have a much smaller spread as opposed to graphs A and B. Now you need to determine whether or not A or B is going to have a larger standard deviation. Well, if we're looking at it in a sense of variability, we can see that graph A has a pretty consistent variability in that from 1 to 10, they have pretty equal chance of occurring, whereas for histogram B, it is bimodal, and so we have both clustered around 1 to 2 and 9 to 10. We have a centralized location where our data is clustered around. Okay, so that brings us to the end of the first lecture. We did cover quite a few topics. Usually I don't cover 5 sections in one lecture video, but I do understand that a lot of this, such as sample mean, a bar graph, a pie chart, are familiar to you, so I felt that it was worth going through several sections rather quickly when those sections are review, particularly when I know certain sections that we're going to go through later in this course are things that you've never seen before, and I'd rather spend more time maybe only focusing on 2 sections for a whole week when the material is very new to you. So for this week, you should begin reading, or you should read rather, Chapter 1, Sections 1 through 5, and you should go ahead and start on your first homework assignment. Some of your first homework assignment is asking you to calculate averages and variances, and at this point you know how to do that, and you should just go ahead and finish it right now. All right, that's it. If you have questions, please send me an email. Have a good night.